So, as a matter of practice, you should be knowing why we are going for the Python and not others. Actually, we can go for the others also, but I have been actually acquainted with the Python for a long time. And one of the most important thing, and also one advantage, is that it's free, and it has like numerous libraries. I can say NumPy, SciPy, and PuLP, which are we are going to use today for our optimization problem. So as you have, it's the third day, you must be knowing what is optimization, and it's important for in mathematics and other application oriented systems. So basically what we perform is the finding one in normal linear programming solutions. We need to find the minimum of a maximum of the solution. So let's start. So this is the first basic equation. So we'll start to do how to program it in Python using NumPy module. So basically I'll use three modules, NumPy and SciPy. And SciPy is mostly used I'm using, and there is another model called PuLP, but PuLP is very specifically that has not been so much developed. I mean, it's not evolved within the research arena. So even if you do not know or do not have Python now, you can keep it later for the practice. So this is the equation. You can see that's a y is equal to x square plus 2x plus 1 with bounding boxes of -5 to 5. So I'll go with the, and I'll go through the Jupyter. Here is my Python workshop. So just first thing first, we have to import a library. So what is not a library? You usually tell it is module. In Python there are various modules, so you have to call as per our requirement. Not in a net, not as in case of MATLAB, we don't have to call any module to directly code it, but in Python we have to actually call a module for its specific functions. For example, here I import the NumPy module. What is NumPy? NumPy is nothing but numerical Python. It has some basic numerical libraries, and how we call it, how we call as a library, I mean module, import NumPy. And how do we import? As NP. Why do we write as NP? Because writing a NumPy every time it will be very lengthy, so it make it short as import NumPy as NP. Secondly, we import another module, that is import matplotlib dot pyplot as plt. What is this matplot? Sorry for that. Okay, so what is this matplotlib module does? Usually it is used it is usually used for the plotting functions as we get in graphs. So here I call two modules which we require for our simple mathematical function. So as I told you, this is our function y is equal to x square plus 2x plus 1. We have to find the minimum. So as I called it as there is no error also. So I again define the minimum bound, which I have already defined in the question, x mean and x max, that is -5 and 5. Then dx is the increment value. What we do in usually we get the derivative. So here for when we program it, we are getting the step function, that is 0.1, or we can write it as increment. Now Now I want to integrate within the maximum bound of x max minus x mean by the increment value, that is 0.1, or we call it as tx. Then we call the function np. You can see here I called numpy as np, so I call np dot line space. Line space, what it does, it generates a set of numbers between the two values, x mean, x max, with increment of n plus 1. After that we call the function which we had defined, which it is our in the question, that is y is equal to x square plus 2x plus 1. So we write here as y is equal to x square. In Python you can see I put double star for the square, single star for the multiplication, plus 2x plus 1. Now I will plot. So how I will plot? If you see that I call the matplotlib.pyplot as plt, so I call the plot function as plt dot plot. Plot is the function. What will plot? X and y. And it will also plot the minimum value. X mean comma x max, that is the bounding value within which it should plot. Okay, let's see what we get. Oops, sorry, this should be actually limit, means it is limited by the boundary, so it's plt dot x limit. You see, the bounding is between the -5 to 5, and this area is the, you can say, the minimum, since we want to minimize the function. Now we will use a while loop to generate the minimum plot. What is the minimum value of this area? So what do? I have another function. I should start with a, this is another one which I should optimize for the 2x square plus 2x minus 22, and it has a bounding values -20 to 20. So what should I do? I need to find the minimum value. Previously we had not find the minimum value, I just plot the function. Now we have to find the minimum value, that is here what is the minimum x mean. We can start x mean as -20, x max as 20, and the increment as 0.1. So again I want to use another function that was in np dot arrange. So what does it do? It starts from one value, that is x mean, stops from at another value, that is x max, and with an increment function of dx, means x mean it will start plus dx, it will go until it reaches x max. So I write the function, that is 2x square plus 2x minus 22. 2 into x square, I give the double star, plus 20 into x minus 22. So again here I get the plot command might be same. I also provide here the grid plot dot grid. You can see the grid also. Now I to provide to get the value, I start with a value called 0 and I iterate the loop using the while loop. How I'll use the while loop syntax, you can use while I of I should be greater than y I plus 1 until it reaches, if the value of y of I is greater than the y I of 1, it should iterate over as I is equal to I plus 1. Give us print x of I and again print y of I. So let's see. You can see it's the -5, the minimum value is -5 and the -72. We have minimized this function within the bounding value of -20 to 20, within -5 to -72 within the of the x values. So back to the presentation, what we next, I want to use this SciPy model. Why you want to use the SciPy model? It is mostly common used for the optimization techniques, and the optimized model in the SciPy, it provides various functions for minimization or maximization objective functions. So what is the optimized functions here? The f mean bound, f mean, minimize scalar and minimize. We will see how we are using those functions. I'll start with another so we'll optimize this function again, but this time we will use the SciPy module. So get the function here again, but we'll first thing is that this time I am importing the SciPy module, not the NumPy or the matplotlib. So what do I write? From SciPy import optimize. Just you see here in the last section I used to import NumPy as MP and import matplotlib.pyplot as PLT. Here I am importing, just I am writing here import, but from here I am writing from SciPy import optimize. It's the various way of following the modules and libraries of the Python. So I give my bounding box here as x mean. We'll have x mean is equal to, again I can give as -5, x max 5. I have defined the bounding box as -5 and 5. Now I have to define the function. How to define the function? I write as diff. I write function y of x. And what should it return? Return x square plus 2x plus 1. X square plus 2 into x plus 1. So define our equation here as a function. So if I call the function, it should return this value. So how should I minimize it? I will write another equation here, and it will call the SciPy function, that is x mean is called to optimize. You see, as I called here, import optimize, that is x mean is called to optimize dot f mean bound. F mean bound is another function under function in the optimize module. F mean bound y, that is our equation, and the bounding boxes x mean and x max. I think there is some error. Yes, I forgot to give the bracket. Okay. Now I want to get the value of the x mean. What should I do? I just write print and x mean. Shift enter, you get the value as -1. So this is the minimum value of the equation within that bounding box of -5 and 5. So this here we call the function of the SciPy and use the optimize value directly without writing the equation here, or writing the, we are replacing this type of equation with one line of equation. So we'll slowly get some complex problem also. So next is, so this is what I showed you now. While when we are calling this function of optimize, these are the parameters it has. That is, it has a minimization of scalar function of one or more variables, where we call as function which called the objective function to be minimized. X0 is the ND array of initial guess, and what type of solver you are using. It may be optimal or minimize or maximal. Then we have bounds, that is bounds on the variables. Here we use the bounds as -5 and 5. Then list of constants. Here we have not used any constants. We will use in the subsequent tasks. So next is, I want to show another one. Actually, we'll go it later. Another one, I want to use the optimization problem using same SciPy module. That is, I have to import both SciPy and the NumPy. So I call here import NumPy as np, SciPy import as optimize. Here I define my objective functions with, I define an objective function here, x1 is equal to x of 0. In Python, we have to be not just to remember that Python starts from 0 and not 1. So every time we have to call something which starts from a value of 1, we have to call it as x of something. Suppose I want to call the first value of an array, then I have to call it as x of 0 and not x of 1. X of 1, it will be the second number or the second value. Similarly, here we are also calling like that. X1 will be the x0 and x2 will be the x of 1. What does it return? It returns the x square, x1 square, x1 square plus x1 into x2. Define the constants also, equality constant. We define it as equality constant of x1. Again we define x1 as x of 0 and x2 as x of 1. And its return is a equation of x cube, so x to the power 3 plus x1 into x2 minus 100. Again I define another inequality constant, that is define equality constant of x having x1 is equal to x of 0 and x2 is equal to x of 1, and it returns x1 square plus x2 minus 50, another constant. Now I define the bounds. Bounds of x1 has been given as minus 100 to 100. Second bound minus 100 to again same. So I combine both the bounds within the as bounds of x1 comma bounds of x2. Now since I have defined the bounds, it's time for the defining the constants. We have two constants here, so I define it as constants 1. Constants 1 is equal to, first is the type, just these are the constants. Fun, that is, you can say fun, x0, method and bounds. So here what type of it is minimization of, then it has a, we define the equation, we define the function which we call it as equality constant. Second constant is the inequality constant, that is constant 2. Yes, you can simply copy and paste. This will be inequality constant, inequality there is some error. I think some spelling mistake, we can okay, it's fine now. So the total constant, we define it as constant 1, constant 2. Another thing we have defined here as x0 value, it's usually to give the define the default bounds which are usually used for this optimization solving, that is n array of initial guess. We are not only giving the one dimensional only, so it is, you see, n d array of initial guess, we give it as 1 and 1. To get the result, what we want to do, we want to minimize the function. So our objective with x0 method this method of SLSQP is just various type of methods are there. We are using SLSQP. We don't have to go into the details here. And here bounds, I give out the same the bounds we have defined in here. Then constant is equal to print the result. There's some error here. Let me see. I called the wrong function here. This should be optimized. From SciPy.optimize, import minimize. That's the reason why it was not able to be called. So it iterated around 96 times, and we see that it's a optimized terminated successfully. The solution was for the optimum value, and it has a value of x1 1.9, so around 2, and x2 as 46. So we'll go for the next one, that is called the Rosenbrock's banana function. This function is defined like this: such f of x of y is equal to a minus x of the whole square plus b y minus x square of the whole square. We will find the minimum of this function. And what is this function is about? This function is about to verify the performance and the robustness of a optimization algorithms. Because if there is a huge highly global minima, there is much more number of local minima, and the global minima is also there, then this function helps to find the optimum solution. So you can see it has a global minima of x of y at a and a square, where the function it is defined minimum at f of x y is equal to 0, and these usual parameters of a and b are set to 1 and 100. Actually I have mistakenly written 100 here. It's 1 and 100, and here in our problem we'll find the minimum of this function. So let's do how it can be done. I select another one. It's a very simple one. Same thing, import SciPy dot optimize as OPT. Here I call the SciPy function of optimization as OPT, making it more short. To define the banana function here, define banana of x a is equal to 1, as I said, b is equal to 100, y is equal to what you see here, a minus x square plus b y minus x square whole square. How do you write? Y is equal to a minus x square, a minus x of square. First value it will take square plus b into y minus x square, b into x of 1. Here x of 0 is equal to x and x of 1 is y. X and y. So x1 minus x of 0 to the power square to the power square. Return y. So I define optimum x opt. It's a variable. So opt dot f mean because we want to minimize the function, where function is the banana function as defined earlier with x0 value bounded by minus 1.2 to 1. Print x opt. So this is the function and its values, minimum values are around 1 and x is 1 and y is also 1 point something. And how many iterations it took? It took 85 iterations and total evaluation at 159. So next we go for the curve fitting. Curve fitting, it's very interesting because if you have some data and if you want to plot a curve or something which should be, why you need to plot it, because we want to mathematically model it, and it's one of the interesting optimization problem. So what we do, we take the data and we plot it mathematically. So we use this equation y of x is equal to a sin x plus b, and we generate some random data, and from the random data using this equation we plot our curve. So let's see how can do. I use this only. So first thing first, import numpy as np. Then from SciPy, here I use numpy, SciPy, matplotlib, three modules for the function. From SciPy dot optimize import curve fit. Then import matplotlib dot pyplot as PLT. Why we need it? We need for plotting. Then we define the variables. So let's start x start at 0, then stop at 2 pi. So 2 np dot pi. If I directly write pi, it won't recognize. From the numpy, it will recognize it as the pi. Then with increment, we have already also used the increment like dx. Here we are directly writing as increment of 0.5. Now I get the arrange. Previously also I had used the np arrange. What does it do? It provides the value from start to stop with increment value. It will start at 0, it will stop at 2 into pi with each value difference of 0.5. We define a is equal to 2, b is equal to now again I am calling another function, that is np.random. What does it do? It generates random numbers. I also introduce some noise in the system. The noise is with a value of 0.2 and it is normal in distribution. Okay, the noise is random distribution, normal distribution, and we define the size of as x. I missed the random here. Okay. Now we define an equation. This is y is equal to a sine x plus b. So write it as y is equal to a into np into sine x plus b. We also add some noise. Y is equal to y plus y noise. Now I define our model. We define it as right is our model of it takes two arguments, sorry, 3, x, a and b. and returns the value of y. What is y? A into np sine of x plus b. X plus b. Then again return y. Now to get the optimal solution, POPT, P COP, we define the two-dimensional array by calling the curve model curve fit from the SciPy module model x y. Let's see what's the value of the p print opt. Okay, so the value is coming, but it is stored in that its memory. We can use it later. Now I define the increment again. To fit the model, I must fit the data in the curve. So here I call the x model data is equal to np dot arrange. It will again start, stop, and what is the increment. Every time I call the np dot arrange, these three are must: the starting value, the stop value, and the increment value. Then I provide the y model of model data, comma transpose of POPT. Again the plot PLT dot plot x model data, comma y model. Actually its model has been generated, but I am not getting the data. So let's see if I get here. Okay. So PAPD value is 1.9 and the P count value is 2.0. To plot it, I have to write it again. Increment is equal to 0.1, X model data is equal to np.arrange start stop increment. Y model is equal to model X model data, then PLT dot plot. Oh, I missed some parameters here. X model data comma Y model. For plotting we need two arguments. I just gave one only. Anyway, I think I'm not getting the data which we have generated using the random value. Okay, we'll see it just in a minute. Just copy the code and start it again here. So actually it should look there like this. These red ones are the random values we have generated, and this the blue line is the curve fitting. So this, according to the red values, we are curve fitting the blue lines. So I don't know why we are not getting here. Anyway, this is the result what we must get. So we'll go next actually. So the next one is the least square method. It's a very popular method which every optimization we used to know. So in the least square method, it requires it's a linear one. Actually, there is a set of data and we have to plot it. It should fit to the linear scale. And the least square method requires the model that should be set up in the following form based on the y is equal to this phi and theta. And the least square method, the function is given by this formula, phi of transpose into phi to the whole power inverse, and again to multiply to the phi of transpose into the function y. So this is the set of data we have, that is y is equal to ax plus b. We generally use to y is equal to mx plus c. So our aim is to find the a and b. So these are the following data where x is given and y is also. So what are the values? Y is equal to ax plus b. This is y value, ax plus b. So we write it is in this form, y is equal to phi comma theta, this and this value. So 15, 10, we have this value 15, 10, 9, 6, 6, 2, 0. This is y is equal to phi. Phi is nothing but the coefficients of a and b, that is 0, 1, 1, 1, 2, 1, 3, 1, 4, 1 and 5, 1, and this is the array a and b. And what is the least LSM equation? This equation we have to fit the data according to this value. So let's go for it. Very simple. I go for another Python. Here I don't use the SciPy or the matplotlib. I directly only use the import numpy as np, and I define py. Py is equal to array. It's np dot array of values 0, 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, and 5, 1. So I write it as 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, and 5, 1. This is the phi. So y, again we define it as y is equal to again np dot array of 15, 10, 15, 10, 9, 6, 2, 0, 15, 10, 9, 6, 2, and
Hello, sir.
Yeah. Hello.
Sir,
Hello.
you've written phi equal to np array. You've written it should be array.
Oh, sorry for that. Thank you. So what is it? 15, 10, 9, 6, 2, and 0. 15, 10, 9, 6, 2, and 0. 15, 10, 9, 6, 2, 0. Okay. There's some, let me see.
Square bracket 1, yes.
It's 1. Here also 1. 15, 10. Oh, fine. So I give theta of ls is equal to, here is that function, theta of ls is equal to phi of transfer into phi. So we directly call it in the function as linear algebra, that is in the linear IALG for LST square S cube S LST square S cube, where you define as phi comma y comma, we give no condition here, none, zero. So actually that is directly the function we are calling from the linear algebra of the numpy. This is the inbuilt function we are directly calling. We are not writing and again the, but we can write, let's say here, theta of ls is equal to np dot linear edge dot inverse of phi dot transpose into, again numpy array of matrix of phi into phi dot transpose again into y. So I can delete this, we don't require. Print theta of ls. So this is the value for the least square method. So it's very small, this one. And if you want to use the this function also, it will give the same result. Let's see if it is giving the same result or not. Yes, the same result. So this is the least square method. You can, that is also called as the regression method. From the set of data you find the linear regression. Now I go for the finding a root. How to find the root? They are from any non-linear objective function. Here I take the objective function as x square plus c cos x of is equal to 0. So I get another one. Same thing. I don't require any special models here. Simply numpy will be fine. Import numpy as np okay. SciPy will be fine. I am using the SciPy here. SciPy dot, because we are optimizing, we need to find the loop. Import root. Import, okay, sorry. What do I do? I define a function of x and it should return particular, that is x square plus c cos x is equal to 0 plus c. We have not defined any c. The constant as, take constant it as 2 or anything you can take, into, since it's a cos function, we have to call the numpy np dot cos of x. And what will give the solution? Solution is equal to root of, because it's the inbuilt function, it will be easy for our calculation. Function with a, we give any coefficient, let's say 0.3. I think I did a mistake in the presentation. It should be 2x. The 2x plus c cos x is equal to 0. So let me see. Is it any problem? Yeah, fine. So I can print the solution here. Print. So you see, it is telling that the solution is converged. at I think 10 and its value at -2 and -3. Okay, we find the root here. So we go for the next one, that is called the Bayesian optimization. So what is this Bayesian optimization? So Bayesian optimization, if there are too many local minima or numerous data and the linear regression does not work. Suppose you have a lot of data scattered form, you are not able to plot it in a linear regression form. We need a Bayesian optimization. Here there is one equation, that is x square into sine of 5 pi x to the power 6, and where x belongs to the real number bounded by 0 and 1. And here in this example we will consider the Gaussian noise with a mean 0 and a standard deviation of 0.1. I can go for another one. Since we are going for Gaussian noise, standard deviation and others, we have to call a lot of NumPy modules. I call first the import NumPy as from NumPy import arrange. We have been using arrange many times. From NumPy again import argument of max, that is argmax. Again from NumPy dot random import normal, that is the normal distribution. And from matplot import pyplot. We usually recall it as from matplotlib.pyplot import as PLT. Here we are directly importing as from matplotlib import pyplot. Both can be used. Again import math, this is another module. It is actually inbuilt, we don't have to install it again in the Python. Import sine, import from math import from math import pi. So these are the models we have imported. Define the objective function. What is the objective function? X comma having the noise of 0.1. So we define the value of the noise, that is noise is normal distributed. We can make it normal starts from 0, scale is equal to noise. What it returns x square sine f by x, sine 5 pi x to the power 6. So that is x square into sine of 5 pi x, 5 into 5 into x to the power 6. And we add also noise. So here you can see we are not recalling the np dot sine, np dot pi or np dot noise, because we have directly called the sine and pi. We don't have to specifically call the numpy function to that is a np dot sine or np dot pi. You can directly use that the sine, pi or pi plot. You see here we have called here the module as from MATLAB import pyplot. We will be using a directly pyplot dot the functions. We will see. Now x is equal to again arrange. We used to write np dot arrange, but here you see from numpy import arrange. I don't have to specifically give np dot arrange or something like that. 0 0 is start, 1 end, and 0.01 means the step. That is we are giving the sampling. Then we define the objective function. Objective of x comma x comma 0 for x in you just have to give it x in x. Then I add the noise again, same objective of x for x in x. To find the best of the solution, we keep this arg of max. So here I just define any number ix is equal to argument of maximum value of y, gives the optimum value of the y. So all correct, good. Now I have to print the optimum value, which I can write it as optima of x. It should be within the integer. We give only 3 decimal points. Y is equal to again up to 3 decimal point with the value of x of ix, which is giving the best of the value, comma y of x. So here we get the global minima of the Bayesian optimization at x is equal to 0.9 and y is equal to 0.8. But then we have to plot it. How to plot? We directly call it as PyPlot. We are not using the PLT. We use the scatter plot. Scatter of we have two arguments, x comma and noise, y noise. Again PyPlot dot plot x comma this x comma y. We plot dot so you see here these dots, they are random values and they are not in a linear scale. We cannot define in a linear scale. For that we need the Bayesian function. So the Bayesian function, what did it do? Since it's a non-linear function, it helps in getting the its non-linear regression, and it has a multiple, you can see, minima, local minimas. So this Bayesian function is very useful when you have nonlinear set of values and you want to make a curve fitting model. Okay, we'll proceed further. I want to take some break. We'll meet again at 10-15 minutes.
Okay, sir.
Okay, thank you.
We'll join in 15 minutes.
Hello, everybody.
That's a good afternoon.
Uh, Good afternoon, sir. So, shall I resume?
Okay, sir.
Thank you. So, I just completed the Bayesian optimization, just showed the Python programming. So next, we are going for a linear linear programming on using PuLP module. Why we are going a PuLP module? Because there has been a lot of this PuLP actually uh, gives the good solver for a SciPy problem, and it has a great interpretability. Suppose we want to change our functions to other, so PuLP gives a better portability than others. And there are other also like GLPK, Cplex, give a bit, but presently there is a demand for the PuLP, so we think we should go for the PuLP and will solve a linear equation with having constants using the PuLP. So this is the equation. It has to minimize, that is x is equal to 3x plus 5y subject to the constants 2x plus 3y greater than equal to 12 and minus x plus y is less than equal to 3, x should be greater than equal to 4, y is less than equal to 3 and both x and y are greater than equal to 0. So as we know that in case of a linear program there is three objectives, that is called the decision variables, objectives and the constants. So here our decision variables are x and y and we have to minimize. Our objective is to minimize this equation with the following constants. So let's go for it. I select another one, close this. Okay, here as I said I am introducing to PuLP. If we do not have PuLP in the linear Python system, we can easily install it as pip install PuLP and it will work fine. So import PuLP as p. We are not importing anything more, nor the numpy, nor the matplotlib, anything else. So what we will do here, we have to minimize. So we have to create. So the commands here are a little bit complex here. LP prop, that is p, that is we are calling the PuLP as p, so it's p dot lp problem defined it as problem, and what we are going to do, we are going to minimize it. LP minimize. These are inbuilt functions. We can go to the PuLP documentation, we can see there. So this is what our work is to minimize the decision variable. Next is creating the problem variables, that is x. X is equal to, again calling p dot lp variable, the arguments are given like that. X lower bound is the 0. Here what we are doing, we are creating a variable x, that is it should be greater than equal to 0. Then similarly we will create the y also. I just copy the code, is equal to, we just give it y low bound is equal to 0, right? Then we define our objective function. So what is the objective function? Objective function is the z is equal to 3x plus 5y. So lp prop is equal to 3 into x plus 5 into y. Now we want to define our constants. So there are how many constants? 1, 2, 3, 4. Already we defined it. four constants. So define LP prob again plus equal to first one is 2x plus 3y greater than equal to 12. 2 into x plus 3 into y greater than equal to 12. One more. Minus x plus y less than equal to 3. So minus of x plus y less than equal to 3. One more. X should be greater than equal to 4. X greater than equal to 4. And y should be less than equal to 3. Y less than equal to 3. So we define it. Let's print and all fine or not print or LP problem. Okay, this is the function. We have all defined the parameters and the constants and the problem variables. Now what we want? We want to solve it. So our status is defined as LP prob dot solve. Actually is the solver, directly it can solve. So now print p dot value of x comma p dot value of y, again p dot value of LP prob dot our objectives. What is the objective? Objective. So what should we get? It gets the value. The optimal solution for x and y. So this is we solved this equation using this PuLP module. You can see in a very few steps we are able to solve the linear equation with having the constants and the objective functions, all the different parameters. So in few lines we get the answer directly. Now we will go for another example using the PuLP, that is diet problem. How can we use the linear program to decide on lowest cost of a diet based on two choices? Suppose I go to a restaurant, I get chicken, I have chicken and peanut butter, and the price of this has been defined here. You can see the chicken gives the 4 units of protein per kg, having the price of rupees 300 per kg, whereas the peanut butter gives 2 units of protein per kg with a price of 200 per kg. Well, I don't know the price. So what is our decision? Decision is has to get the we want to get the protein actually. How much in low cost we want to get the optimum level of protein. The minimum amount is 8 units. We want a person goes and he wants to get 8 units of protein. He has a choice of these two, chicken and peanut butter. Now he has to choose by linear programming whether it is able to solve at how much price and what should be the choice of getting both peanut and chicken and peanut butter or combination of both. Let's solve this problem. And so here we define the decision variables. Decision variables are two decision variables, that is x1 peanut butter and x2 the chicken. And what is our objective? Objective is to minimize the total cost, and let's say x1 into 300 or x2 into 200. This the constant is satisfy minimum protein intake, and this is the. So how do we define the constant? Minus 2 into x1 y 2 into peanut butter 2 into x1 is this is 200, then 4 into x2. Sorry, we don't know the value of the x1 x2, we have to find out. So let's find out, but the our aim is that it should be greater than or equal to 8, because we want to get 8 units of protein. So let's solve that. How do we solve it? I close it out. New, go to another Python. So we get from PuLP import star. So we are directly calling the function star from the PuLP. We don't have to call it again and again. Directly we will use the function using its local variables whatever in the libraries. So I just call it as import star. So what is the problem? I define the problem as PuLP dot lp problem about diet. We will minimize the price. Minimize. So what are decision variables? Two decision variables are there, defined as xp lp variable. We have chicken lp integer. Then again I call lp variable peanut butter. lp integer. So these are decision variables. Now define the objective functions. So what are the objective functions? Prob is equal to x1 into 300 plus x2 is the peanut butter price is 200 gives the total cost. Another constant, that is 2 into x of 1 plus 2 into x of 1 plus 4 into x of 2 must be greater than equal to 8 because we want minimum protein intake, that is minimum protein intake. Okay, let's see. Okay, is there any problem? x1 into 300 plus x2 into 200 gives the total cost. Problem 2 x1 plus 4x2 greater than equal to 8. Okay, so missed a comma here. So what is the status? Is to solve the problem. Problem dot solve. We are giving the default values and it will solve accordingly. Then LP status of status. What is that's the value of the last iteration. Then we will get the hint of solved problem. Again print of value of x1 comma value of x2, that is chicken, then value of the objective, prop dot objective. What is objective? How do you get? So here you go. So you see, this is the value we need. This is the peanut, chicken, and this is the price. Not price. 400. So we can see here that we don't need peanut butter. If we want to get the optimum value of our money, we can use two chickens to satisfy our protein intake. No peanut butter is required. So this is how we solve a dietary problem. This is a simple example. We'll go for another practical example, that is called the constant box problem. So in the constant box problem, what we'll go, okay, let's go. In the constant box problem, it is given that there is a paper and you have to give that what is the value of the length of the sheet, so that you can have the highest volume. You will fold at such a length that you will get the highest volume. You have a sheet, and from the sheet you can get the length. So what should be the length that you get the highest value of the volume from the box you are making it. So we'll see that. Go for another. So something we import something that is import numpy as mp. Again we import SciPy as sp and import matplotlib dot pyplot as plt. So we need to describe the variables. What is the length of the sheet, that is L is equal to 30 units, and we arrange we sample it, and we can sample it by calling the numpy function with range space, that is start from 0 to L by 2. That is the maximum value. You cannot go beyond that, otherwise there is no point of making any volume box. And the step size is 2 to the power 10, getting a very used step size here. So I think we all must be getting what is the difference between line space and the arrange. Arrange is start, here stop with a step size. The line space, the start, stop, and this number of steps it should make. It is not the step size. V is equal to lambda. To define the objective functions, you can use lambda in the SciPy module. X comma L, and L have a dimension limitation of L minus 2 into X to the power 2 into X. Okay, now define figure is equal to PLT dot figure. And define anything we can give. I give it as 5,4. 5,4. Then define the title. These are nothing but just to make the graph look easy and good. So we give the title as volume as a function of X. plt dot plot x comma v volume of x comma l we label it as leave it, we don't want to label it. Then I can plot dot plt dot scatter with L by 6 comma L by 6 0 again v of L by 6. L by 6 comma L by 6 0 comma v of L by 6 comma L and give some basis. If w is equal to 2 comma some, now we can give as z having order of 15. Sorry for the mistakes, I just directly copy the code. You can see. Anyway, this is actually, there is some error. You can edit it later. So this peak, you can see it is the L by 6. The 6, it's the value of the length of the sheet from where we can make the maximum of the volume from a given sheet of paper or a cartoon to make it the highest volume. So this total, this plot is around L by 2, and the peak is the L by 6 from this place. So we'll proceed later. Sorry for this mistake. So next we come as the, that is very important for our topic, that is the ant bee colony optimization. So what is called the ant bee colony optimization? It is a probabilistic technique for solving computational problems, of course, which we can reduce to finding good paths through graphs. So where it is getting inspired? It is getting inspired from the behavior of the real ants. So what the real ants do, they search for the food. It can be either any sweet things or whatever may be. So what they do, they always search for the food, and in the time they randomly go to a place, and in the subsequent time we see that they make a uniform path, and that uniform path they all, most of the ants they follow. And but how do they reach that uniform path? And this from that their behavior, this mathematical model has been derived. But the one of the advantage or disadvantage whatever may be, it is not necessary, does not find the shortest path. The path what they follow does not necessarily mean that it is the shortest path. So how do they follow? So one of the most famous problem is the traveling salesman problem they used to do. So this is the algorithm. So initially they will follow the random path. So after that, they depending upon the visibility factor and the pheromone strength. Pheromone strength is the, wherever the ants pass, they pass pheromones, means they pass something so that the other ants can detect and they can travel to the path. When more and more number of ants they pass through one area, the strength of the pheromone increases. So if the intensity of the pheromone is higher, then more number of ants will follow the path. And if two ants go by two different paths but cross at some edges, there will be some pheromone intensity increase, and at these paths there will be more other ants, they will follow more often. So this is the overall uh, algorithm of the ant bee colony. So what they do, what we do, we go to a random place, we place ants at the cities, randomly place ants at various cities. For each ant we choose that it choose a not yet visited city until one tour is completed. Then we optimize the tour and update the pheromone strength. After they have established the path, pheromone is evaporate the pheromone. So how do we solve it? First, first is we define the place of the cities, random cities. So here we define the models as import numpy as np, and again from numpy import inf infinity. The infinity was imported because there will be division by 0 and it may lead to error. So to minimize that error or to neglect that error, we call the numpy function from and import the infinity function. So now first we do what we do. First we define the cities. So cities are np dot array, that is define random city, let's say 0, 10, 12, 11 and 14. I think let's go whatever I have completed it. D is the distance between the cities. Then we define the number of iterations. Iterations is equal to 100. And how many ants we choose? In your problem we choose 5 ants. And ants is equal to 5. And how many cities? This is 1, 2, 3, 4, 5 cities. Now we define the number of ants is equal to n ants. Cities is equal to n cities. And is the evaporator rate of the pheromone, that is 0.5. 0.5. Alpha is the pheromone factor, that is 1. Beta is the beta is the visibility factor, 2. Then we calculate define the visibility. Visibility is the shortest distance when the ants see their food. And visibility factor is calculated between the two cities also. If the visibility is equal to infinity, we define as visibility is equal to 0. So we can neglect this, because for that reason only we imported the infinity function. Now pheromone is equal to, define initialize depending on how many matrices, that ones of np dot ones of m comma n. M is the number of ants, N is the number of cities. Now initialize the root. What is root? Root is the position of the ants where they will start from the location, first location. So root is also defined as np dot same comma n plus 1 sorry, this is multiplication. Here is multiplication. Now we have defined all the variables. We need to iterate. So for iterating, I am just giving the code. I am just copy pasting so that you can understand easily and quickly. Let me check if it is correct. I'm just opening the my spider where I can directly show you. It's a long one, so I need to put the problem here. So here you can see not directly the code. I just want to explain it since it is not, it's a long one. So here see, in each iteration what it does, it updates the pheromone, it updates the visibility factor, and it also combines the visibility factor and the pheromone to update it element by element. So let me start here where I have left. This is the root where all the ants will start from the location 1, and as I said, these are meta-heuristic search algorithms used for combinational optimization. This code just I need to explain you in briefly. So here we define the root. Now in each iteration the root is initialized from for 1 at 1, then again within the iteration another iteration is made so that the for visibility factor, we are creating a copy, and we are again adding that copy in that current location, and in each iteration we see that we are calculating the pheromone factor, calculating the visibility factor, and that the axis we can see that size of 5:1. It is updated every iterations. So this iteration continues for 100 times. We have defined it 100 here. So after that, what we get is that pheromone and the visibility factor are updated, and we can get the value of the directly I get here. Best path is the 1 2 5 4 3 1. That is the city, and the best path is equal to the 55 on the 55 number maybe iterations. So basically, actually I have not been so much clear with this and B colony. Just for demonstration I have showed you. So each time I iterate, there may be some different values. We can see the path is 52, here it is 55, based on the best possible iterations. So another, I think I will go to the, so this is the I just before described what is the what we do actually in the ant bee colony optimization. This is the algorithm and the code I showed you. Next we go for the genetic algorithm. I think Samina I just described briefly. I mean comprehensive. I will describe just briefly. This is the genetic algorithm where we do this the following. Means the population is calculated, then the fitness calculation, the mating pool, then the parents are selected, then mating crossover are done, and then the offspring. So one equation we will try to do here, that is, this is the equation, y is equal to w1 x1 till w6 into x6, where the x value of x is defined as 4 minus 2, 3.5, 5 minus 11 and minus 4.7. So our aim is to find the best value of the weights, that is w1 to w6. So we have this code here. In the code, what we need the fitness function, the mating pool, crossover, and the mutations. Each time this has to be updated so that in case of any actually the genetic in case of any good offspring, they will select that best. So what we do in a genetic algorithm, we actually start from the population, then we create a population, we randomly generate the solutions, we code it as binary arrays and score the fitness function of the of each individual. Then we loop it. For what? To loop it in the better, to get the better parents, and generate two child solutions from two parents, mixing the genes from each parent, and by applying a chance of random mutation. Why we are applying a mutation? So that we expect that the quality of some of the genes, good quality genes, will become more qualitative. Then the same procedure is repeated for every child until a new population size is reached. So this goes on again and again. This is a function what we have defined here for calculating fitness function, calculating mating pool, y, to select the best individuals in the current generation. Then the crossover, because the next offspring they will come. Then we induce some mutation each in each generation to get a good value in the next generation. So I will directly go to the solution. uh, as I said, our target is to minimize this function, and we should get the weights 6, this w1 to w6 of the optimum value of the weights. So as I said, the input equations: 4 minus 2 3.5, 5 minus 11 minus 4.7. Weights we are giving 6, there are 6 weights, and solution for population, that is 8, means 8 chromosomes are there. Then number of parents are there, we define 4. Then we define the population size, where each chromosome had the numerical weights generated. Next step is the creation of initial population. Then the number of generations what we want to get is 5. That is number of generations is not number of iterations. So in iterations we call the functions here. The function defined here earlier: fitness function, mating pool, crossover, and mutation. And we get the latest fitness function, that is the fitness is calculated for each solution in the final generation. So the best solution we get it as from these weights. It is the 63.5 is the best solution among the, and the best population is this one, and the best solution is the best fitness is the 63.5. So this is one of the simplest form of the what you call genetic algorithm. So I have another genetic algorithm also. But I think it's not required to explain here. I think I can conclude here. This means completed my all the whatever I wanted to demonstrate. Okay. So here's Karan madam and everyone. Like this is my conclusion. I stop here.
So participants, do you have any questions? You can ask.
If someone wants the code and everything, I can provide them. Then you want, I have provide the email. They can email me. I will just mail them all the codes with the explanations, whatever I have explained today.
So on the behalf of the Triple Department, SSTC, SHGI, I would like to take this opportunity to thank you for the wonderful presentation you gave today. So we are grateful for the time and the effort you took to share with us. It is extremely informative session. Looking forward for our future interaction, sir. So once again, I would like to thank you, sir, for taking your time from your busy schedule and enlightening us with your knowledge. Thank you, sir. Thank you very much, sir.
Thank you, sir. Thank you a lot, and thank you for the Sankaracharya Technical Campus for giving me the opportunity. And thank you if I can help in the future.
Okay,
And
sir.
I hope if any student require, they can contact me for in this Python
Okay.
explanations. Thank you.
Thank you very much, sir. Thank you.
Thank you.
Okay. So participants, we will meet tomorrow at 9:30 a.m.
Hello, hello, sir.
Hello.
Sir, actually, I have a question to sir.
Please, please.
Please, please. Yeah.
Sir, actually, I am also working in the optimization area, and for that, I am using Gurobi optimizer. Sir,
Gurobi. Okay.
yes.
Actually,
So,
I have Gurobi. I heard, but I have not used. Usually, this is actually work in FPCA, and for my neural network, I have not used that. But if you ask me, I can go for that. What is that you said?
I am the beginner to that Gurobi optimizer. So some of my colleague told that this is a good